Most people assume the universe rotates. This seems almost inevitable. Rotation is everywhere. Planets rotate, stars rotate, galaxies rotate, and entire solar systems move through space with their own patterns of motion. Rotation seems so natural that it's easy to imagine the universe itself spinning like a giant cosmic wheel. For centuries, this idea was almost self-evident. But the strange discovery isn't that scientists are searching for cosmic rotation. The strange discovery is that after decades of measurements, the universe rotates so little that it behaves as if it hardly rotates at all. And this subtle difference between not rotating and rotating almost invisibly reveals a much deeper mystery of why rotation exists. Almost every large object we observe in space carries angular momentum. The Earth rotates, Jupiter spins rapidly, the Sun rotates, and giant gas clouds begin to rotate as they transform into stars. When matter comes together, rotation seems to naturally arise. Once something starts rotating, it's surprisingly difficult to stop. This simple rule explains everything from an ice skater retracting their arms to the formation of rapidly spinning neutron stars. The universe seems to be full of rotating objects because rotation is one of the most enduring behaviors in nature. But this raises an unexpected question. If everything around us is rotating, where did all this motion come from? At first, the answer seems simple. Objects inherit motion from previous structures. Planets inherit motion from the disks that form them. These disks, in turn, inherit motion from larger gas clouds. But if we trace the chain backward, we arrive at a strange place. The early universe is incredibly smooth. Observations of the young cosmos show an almost homogeneous distribution of matter and energy, with only minor differences between regions. In such a smooth beginning, explaining large-scale rotation becomes much more difficult. This question becomes even more intriguing when scientists begin to ask whether the entire universe has a preferred direction. If the cosmos itself is rotating, it should leave traces of that motion. Light passing through different directions is slightly different. The arrangement of galaxies should reveal a hidden cosmic axis. The universe wouldn't look the same everywhere. Even some solutions in Einstein's equations allowed for this possibility.
In 1949, mathematician Kurt Gödel described a rotating universe model that was mathematically possible, but the consequences were strange. In this model, space-time could twist in ways that allowed paths through time itself to behave unexpectedly. The mathematics worked, but the result felt completely different from the universe we experience. The idea showed something important. Physics did not completely forbid a rotating universe. Reality simply seemed not to choose that path. Then astronomy entered a new era. Telescopes became more powerful, and scientists gained access to one of the most valuable pieces of evidence in cosmology, the cosmic microwave background. This ancient radiation, discovered in the 1960s and later mapped by missions such as COBE, WMAP, and Planck, gave researchers a view of the universe when it was extremely young. If the universe had significant rotation, this radiation should reveal it. Scientists searched for patterns. They looked for asymmetries, preferred directions, and subtle distortions across the sky. But the result was almost the opposite of what a rotating universe would suggest. The cosmos looked remarkably uniform. In every direction, it appeared nearly the same. The expected signs of large-scale rotation were missing. Yet, this did not end the mystery. It created a new one. Local structures spin everywhere. Galaxies rotate, stars rotate, planetary systems rotate, but the largest structure of all appears almost still. Somewhere between the scale of individual objects and the scale of the entire cosmos, the rules seem to change. Imagine a calm ocean filled with countless whirlpools. Each whirlpool rotates, but the ocean itself does not need to spin as a whole. Something similar may be happening in the universe. Rotation can emerge locally without requiring the entire cosmos to rotate. As scientists built more detailed simulations, this explanation became stronger. Small irregularities in the early universe grew through gravity, forming galaxies and larger structures. During this process, interactions between different regions naturally created angular momentum. Galaxies did not need a rotating universe to gain their spin. Their motion could emerge from billions of years of gravitational interactions. But this answer created an even deeper question. If rotation appears so easily, why does it appear so often? Why does matter almost seem to prefer organizing itself into spinning systems? The answer is connected to one of the most fundamental ideas in physics: symmetry. Angular momentum is not just a property of moving objects. It is connected to the fact that the laws of physics do not change depending on how we rotate our perspective. The work of Emmy Noether in the early 20th century revealed a profound connection between symmetry and conservation laws. Rotation survives not because the universe has a preference for spinning objects, but because the structure of reality itself allows this behavior to persist. Suddenly, the mystery changes. The question is no longer why galaxies spin. The question becomes why the universe does not. If rotation is naturally allowed, if physics permits rotating models, and if angular momentum appears everywhere, then the remarkable feature may be the universe's incredible balance. Researchers still examine this possibility today by studying galaxy distributions, cosmic radiation, and subtle patterns in astronomical data. Occasionally, unusual observations raise questions about whether hidden directional effects exist. Most disappear after more careful analysis, but the search continues because understanding why the universe appears so balanced could reveal something about its earliest moments. The deeper lesson is that our intuition often assumes large patterns require large causes. We see countless galaxies spinning and imagine the entire cosmos must share the same motion. But nature works differently. Complex structures can emerge without a larger version of themselves controlling them. Order can appear without a central design. Motion can exist without the entire system moving. The universe may spin for a reason, just not the reason we expect. Because the real surprise is that the cosmic stage itself may remain almost completely still while everything on it moves. The galaxies are not necessarily pieces of one giant rotating machine. They may simply be the result of simple laws creating extraordinary complexity over billions of years. And perhaps the most fascinating part is that this does not make the universe less mysterious. It makes it stranger. A cosmos where everything rotates except the cosmos itself challenges one of our deepest assumptions, that the largest things must behave like larger versions of the smaller things inside them. And if something as familiar as rotation can completely change meaning when we look closer, it raises a much larger question. How many other things in the universe do we think we understand only because they look familiar from a distance?